Alright, physics video. See how long the battery lasts. This may be a long one. It might last an hour or so. It's probably all you're going to get out of it. But might take a while. So I did attempt discussion of physics with Piro, but it's pointless. See, you can't make a single argument that is ever held as a, okay, let's establish that as a foundation to build on. So he will accept no arguments that get to the point that physics is built on some shaky ground in certain areas. The double slit experiment, gravitational lensing, is a few. There's a lot of them actually. Dark matter, dark energy. You can go through all this, the list. The black holes. There's a lot of stuff that's very weak evidence that they have drawn hard conclusions based on weak evidence. And certainly if you go back to the question of light being a particle or a wave, and the whole bad compromise of particle-wave duality, the evidence is just absolutely rotten. And what is being argued by physicists is rotten. And so I'll play some of a MIT lecture just to display some of the rottenness of this as a foundation for confidence. And because it's bad. I mean, for especially physicists should be the most disciplined of scientists in a way, and they're the least disciplined by obvious problems. It's almost like computer code. It's intolerant to errors in a lot of ways, especially in the old days. Zero tolerance. And so most of the programmers who did programming in the old days kind of understand that zero tolerance for errors. And as soon as you see something that looks like an error, you fix it. You don't just say, whatever, close enough. And so I can't come up with a metaphor to really describe this situation. But it's a profound problem in physics that when lay people can do a small amount of research and detect glaring misrepresentations of the truth made by people like Feynman and MIT lecturers, that's a problem. It's a big problem. So anyway, so back to the Piro conversation. So in this conversation, I went through this whole thing with Piro, explained the weakness of this evidence, the fact that, yes, if you look at water waves, you can see a similarity in the fact that you'll get an interference pattern with two water waves in a two-slit experiment. But there's no similarity when you do a single slit. If you do regular water waves without cheating, without creating noise in the waves, regular water waves going through a single slit will not have any interference pattern. And with a double slit they will have an interference pattern. So let's understand the pattern is just on, off, on, off, on, off, on, off. And there's the brightness of the middle on is brighter in one experiment than the other, but otherwise the proportionalities are exactly the same in both experiments, single slit, double slit. You get exactly the same pattern, it's just in the single slit the central maxima is much brighter. And the truth is, in water you don't get that. So it's like Newton's rings. Newton's rings don't happen. When you put light through a small aperture, you'll get on-off. Okay, so it's the same as a slit, it's just in a circular manner. So this is your on, off. Same thing. Water won't do that. So so they have something that's similar in water, and so they draw a conclusion. Oh, it looks like water waves, therefore it's water waves. But it doesn't look like water waves in a single slit. It looks nothing like it. No similarity whatsoever. Nothing in common. Nothing. And that's the true context here. Let's also understand that the real pattern, okay, when you create a double slit pattern, it does this kind of thing. Draw the picture and then I'll show you the picture, but you kind of know it. It does this thing, okay? The on-off happens here in the middle. It bulges and then it bulges and then it bulges and it bulges. So it has these, it has a superimposed pattern on the pattern, and that is not in the mathematics. So when you do the mathematics of the double slit experiment, there's no bulges. Not there. That should be something to open people's eyes. The original Young experiment, if you go and look at what the actual images of the actual Young experiment look like, they were done with sunlight, so it wasn't monochromatic, it wasn't of one color, so there was blue shift and red shift in the images. And it was basically just a bunch of images of what you could understand to be images of the sun. Yeah, they were like mirror images of the sun. Duplications of it. But anyway, that's a side issue. But this is the experiment for which the whole dispute of wave particle was in some way resolved. Now there's, in my opinion, there's no other evidence of any kind of wave function built into photons. You can't make photons interact with each other. They have no, they don't wave into each other. You can't combine them. You can't do anything that you could do with waves with photons. Now electrons are a little different because electrons are charged, and charged bodies going next to a charged surface are obviously going to be repelled or attracted based on the charge. So it's not really, because electrons behave similar to photons. But that's because they're just showing you what the photons are really doing, which is they're interacting with electrons. So I'll get to that eventually. But the real point of the argument is that before this conversation about a better theory can take place, people can't keep arguing the existence of their God. If I'm arguing for evolution, somebody has to suspend their God theory for a minute and pay attention to the theory of evolution as an explanation, or it's just not going to happen, because they're just going to keep saying things like, well, God made the platypus, and then God did that, and then God did that, instead of paying attention to the progression. And what the evidence indicates is that there was no God interfering, that the biology alone can take care of the problem, and there is an explanation for diffraction that doesn't require you to think photons are waves interfering. No, they're photons diffracting. They diffract to create rainbows, on, off, on, off, on, off. I mean, the color separation you can think of as an on-off pattern. But again, that's another thing. They talk about how, look at the pattern, the pattern, the pattern. The pattern is the simplest pattern you could have. On, off, on, off, on, off, on, off. Can't get simpler than that. Alright, so that's a preliminary statement. So let's play some of this, and I don't want to waste too much time on this, because he just did it twice though. I made these arguments to him. It's like it never happened. Then Numbly Num brings up the subject again. Pyrrho just repeats the same jargon, and this is the part that's so irritating. We already know what the current thinking is, and we're arguing the current thinking has nothing to foundation under it, nothing. And Pyrrho just keeps arguing that somehow water does, in the single slit, done honestly, does diffract, which is the same thing as saying if I poke my finger in a puddle, that somehow I'm going to create interference pattern. And we know I'm not going to. It's the same experiment as the single slit experiment, just poking a puddle of water. And you can poke it all day long, and you're just never going to create an interference pattern.
Fact that the double slit is a late stage thing. The real origin of it is entirely different. It's prior.
Why do you think there's...
So he's saying it's entirely different. Well, then you ought to tell the MIT professor that it's entirely different, because he doesn't think so. And the one at Yale doesn't think so. And I'm pretty sure the one at Stanford doesn't think so.
Single slit. Why do you think you see the same pattern with a single slit then? Like, you know, that becomes the problem with the double slit. It's just that, oh, the single slit produces the same result. So it's
because here's why. If you have a flat wave front, right, so just a totally flat, which you can have, like in water, you have a big block, and you put...
So again, so he's making the same argument that somehow photons are bulging as they go through the slit. That still doesn't explain single slit. So again, he's just ignoring the question, which was directly the difference between the single slit and the double slit. And the single slit in water doesn't create an interference pattern. It does with light or electrons. That's the difference. He just ignored the question, and then it's just going to go on this diatribe again telling us what a wave does when we already know what waves do. So, you know, you're just wasting time.
Push it forward all at once. You create a flat wave front, and it hits a slit.
You know, Young's experiment wasn't a flat wave front. The two-slit experiment traditionally done with electrons or photons was done with an aperture in between the light source and the slits. There was an aperture that created a bulged wavefront. So again, it's irrelevant about your linear wavefront. That just makes it more obvious. It doesn't explain it.
You cut off part of the wavefront. At the edge of the wavefront, the water is going up and down at the edge of the wavefront, just like it is in the middle, which it causes it to push out into water that, you know, is not yet being disturbed, right?
no water.
You see, again, this has nothing. This is him explaining how you have water comes in at straight lines, and it comes out as a bulge with a single slit. And that's all it does. There's no interference pattern created with water waves going through a single slit, unless you use 3 agitators here to create many frequencies of wave going through the slit. So unless you cheat and don't have flat waves coming in, there's no way to do the single slit experiment in water and get in an interference pattern unless you cheat back here. No way.
There's no water that's yet...
Doesn't matter, water. Yeah, no, with light, it's the electromagnetic field. You have the
Right, so the electromagnetic field, blah, 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 blah. So, I mean, it's just a complete... Again, there's just no evidence of any electromagnetic field, except when they want to do this interference stuff. Photons don't electromagnetically interact with anything. You can't give something electricity as a photon passes by. It has no tangential dimensions. As I've pointed out before, a photon is moving the speed of light in one direction. It only has mass in that direction. It is producing nothing in any other tangential perpendicular direction, which is traditionally the only way something can express a magnetic or electric component. They have to actually produce what are called these virtual photons in any other circumstance. They have to create the field by creating something, not nothing. Fields are made of something. This is a problem. They call them virtual photons. I'm just saying, are you going to argue that photons are creating virtual photons? That's going to sound pretty bad, I think.
magnetic field at the end of the wavefront going up and down, which causes it to spread out because it goes laterally, because if you go up and down in one point, it goes out.
All right, well, I'm just not going to waste any more time on this. Obviously, the question was quite clear, okay? If you put linear flat waves into a single slit, they will not create a diffraction pattern in any other media except when you start using photons or electrons. And again, I'll explain that difference. Electrons are charged. Electrons do not like to fly straight. If they're near anything, they're going to get moved by it because they're moved by fields. Quite obviously. They have an electric and magnetic component. Alright, so let's go to the lecture. And, just play this. So this is Professor Lewin. and we'll get into a little bit of Huygens here, but it's just very little, which is a little irritating. It's only used, Huygens only comes up, okay, this idea of, it's a way of turning the single slit experiment into a double slit experiment. So now they can do the math. Now they can create interference. They can explain why there's interference. So it essentially, what Huygens does, it permits you to create a mathematically invisible, a zero width impediment in the single slit experiment. And that's basically what it does. It creates a zero width impediment in the single slit experiment, creating now the opportunity to create your two waves, where you didn't have the opportunity to create two waves, obviously, when it was a single slit. So you turn the single slit into a double slit. And in the math, I won't go through the math part because I would like to, but I'm just doing it because I think it's just going to make the video a little bit boring. But you can simply see where Huygens just means that there's a 2 put into the equation. So all it does is permit the division of the slit into two pieces. And that's what makes the math work, is simply the fact that in the end, all the Huygens talk about all the zillions of infinite waves it creates, in the end, all it does in the math is create the times 2 that you need, or divided by 2, that you need in the mathematical equation to create the 2-ness of the two slits. You need to make the one slit into a 2-slit experiment, and that's what Huygens does.
We'll talk about interference of electromagnetic radiation, and I will start as a warm-up with the famous historical experiment which was first done by Young in 1801.
Right, so 1801, long time ago. Very crude. Basically just a bunch of images of the sun. Yeah, mirror images. Sorry, I want to get more volume here. I don't know why it's not increasing.
By that time, the issue whether or not light was waves or whether it was particles was still unresolved. Newton always wanted light to be particles, but the Dutch physicist Huygens wanted them to be waves, and the issue was unresolved.
Right, Huygens. So this guy is Dutch, and so that's, it seems like it's almost a silliness about him. He always has to point out when a scientist is Dutch. That's a little bit tacky for a scientist. But regardless, and the whole putting it wanted it to be is also kind of bogus. Newton had reasons to believe photons were particles because of the way they behaved. And yes, back then, they, certainly before the 1800s, you can imagine they didn't have huge technology. So sometimes they would draw conclusions, because they didn't have a microscope small enough or a telescope good enough. But there were reasons to believe light, because of the conservation nature of it, was particles. And it's also was believed to be particles because waves are incoherent. You can't draw a wave of light. There'd be no way to form it. There'd be no way, because it's a tiny thing. It can go through tiny holes, light. How does this wave thing do that? How do you have a wave that confines itself? Well, how does the wave not spread? It doesn't fit. Waves are always in mediums, traditionally. So even the very idea of thinking about photons as a wave obliges you almost to think about ethers and all kinds of stuff, because there's no other way to, how do you make it move through the medium? And if you make it a wave again in a medium, why isn't it spreading? How can a photon travel billions of miles, and how did it not spread?
Let us agree that if light are particles, and you have a screen that, say, has two openings, and you would throw tomatoes are particles, and you collect them here, then those tomatoes that don't get stuck on the screen but that make it would form a pile here of tomatoes, and they would form a pile there of tomatoes.
Yes, but that's only if you say, okay, let's forget that we know about diffraction, and forget that we know that electrons are and that molecules of water, for example, diffract light and create rainbows. So let's just pretend that we don't see actual things that bend light. So yes, but yes, if there were tomatoes, that's what you would expect.
Very typical for particles. But the situation is different when we deal with waves, because the moment that you have waves coming in...
Okay, so he used this. Now see, isn't that a little bit of a distortion to say, well, look, here, I have two openings and I'll make two lumps. Couldn't he have just done the one opening and said, look, if I throw tomatoes at that opening, I get a pile of tomato here. Now, we know already from Newton, at Newton's time, Newton did this with a small aperture. So you create a small aperture, you shine light through it, and it diffracts and spreads. So Newton already knew this. So the fact that light was diffracted by a surface was already established. So again, this drawing could have been done with a single slit. And then when he tries to do this wave nonsense, all of a sudden it breaks down, because water waves in a single slit will do exactly this. They'll create the opposite hump. The highest intensity in the center, the lowest in the further away. It travels longer. It comes in out of phase by the time it gets to the further location. But there's no interference.
Say, for instance, we have plane waves coming in like this, then the wave can go through both openings simultaneously, and that changes the picture quite dramatically.
And again, simultaneously implying that a photon goes through both slits, which he's actually going to say, which is, shouldn't that right there, shouldn't the whole room just go quiet and everybody just say, nah, there's got to be a better answer than that, right? Photons are little things. They don't go through both slits. That's silly.
It was known, of course, already in the 17th century that if you have water waves going through a small opening, so here are water waves moving in like so, and here is also water, that what you see coming out there are circular waves.
Right, which you didn't draw, but go ahead and draw them, please. Yes, they're just circular waves. No interference pattern. Single slit, no interference in water waves. Nothing like what Newton observed with the single aperture in the 17th century. Well,
the waves then look like this.
Oh, okay, thank you.
And they're propagating out in a circular fashion. And if the velocity of the waves here is the same as the velocity there, then the wavelength here would be the same as the wavelength there. But if the velocities are different, of course, you will see a change.
Right. No interference, Piero. No interference pattern. Water, single slit, no interference pattern. Light, single slit, interference pattern. Nothing like each other. It's not like water waves.
The difference in the wavelength. So Huygens, my countryman, suggested in the 17th century the idea, which is now known as Huygens' principle.
Everybody says Huygens, and he says it's Hausens, which is kind of funny because he's Dutch, so he knows. But he says it's okay, I'll say it your way later. So later he says Huygens, because he concedes. It's like, why are you doing that? If we're saying it wrong, why don't you tell everybody to fix it? Hausens. I can say Hausens.
That we can think of this in a very different way. Huygens, by the way, is difficult to pronounce.
Hausens? I don't think it's that hard. It sounds like Hausens. It sounds like Hausens. Hausens. I have house and sense in the house. Hausens.
One of you who knows how to say Huygens correctly is also Dutch. Because you miss the R in your language and you miss the in your language.
I didn't hear any of that. But anyway, it doesn't really matter. I guess you're just saying the other thing was in there. Thousands. I can do that. Thousands. Huh?
The combination of ui and is a complete killer for you guys.
Yeah, it's huh.
You don't get extra 803 course credit if you can come to my office and say Huygens, but it will certainly put you in the Dutch category.
Very exciting.
So in the 17th century, then Huygens came with an idea which was later amended by Fresnel in the 19th century, and is now known as the Huygens, I will pronounce it your way, the Huygens-Fresnel principle, which works as follows. If we have a plain monochromatic wave.
Right. Okay. So, yeah, they don't even bother with the Fresnel part. But Fresnel was kind of interesting fellow there. You know, he did lots of interesting things with the. So yes, Fresnel lenses, really interesting stuff.
And it's incident on the screen with an aperture. So this would be an aperture, an opening. Here you would have two apertures, two openings. Then the Huygens-Fresnel principle states the following.
Let's understand, it's a principle, not a law or a rule or a fact. It's just some sort of principle, which in science jargon sometimes doesn't have the same meaning as in like philosophy. In philosophy, a principle is important, but in these things, principles mean, well, maybe we just made this part up.
Points in the aperture plane may be thought of as secondary point sources of spherical waves.
Right, so what they're basically saying is a wave comes in and zillions of waves go out. And then all the other little zillions of waves interfere with each other, negate each other, and there's only two left at the end. The two at the ends. How convenient! We just turned a single slit into the double slit.
And the point sources replace the real source, which is flooding the screen, and the screen itself is a perfect absorber of the radiation falling upon it. And so I will repeat the Huygens-Fresnel principle, which...
Yes, thank you. Just understand that they don't use the Huygens-Fresnel principle when it's two slits. So they only use it when there's a single slit because they need to make two sources. So when they have the double slit, they don't need the two sources. And if they use the Huygens, so if they use the same to be consistent, if they were consistent, which is sort of the rule of physics, right? It's consistency of principles. You can't have a principle, use it here, and not use it everywhere else. Then it's called bullshit. So if you're only using it in one circumstance, that's called fudge. Okay? It's sort of like dark matter. When dark matter only exists to create lensing explanations, and you can't explain how it doesn't have any gravity that's, you know, forcing the galaxy to spin funny, that's called bullshit. And it's bullshit to say Huygens exists when we're doing a single slit, Huygens doesn't exist when we're doing a double slit, because know what would happen if they used Huygens in the double slit experiment? It would turn it into the four slit experiment. Yeah, and then it would come out wrong.
I will need today. All points in the aperture plane may be thought of as secondary point sources of spherical waves.
Right, so they're saying all the points inside of this little thing here. And he uses the word infinite. So there's an infinite point sources in that little tiny gap. And so you can just make as many as you want. You want to make 10, make 4 zillion, it's okay, doesn't matter. There's an infinite number of them, and guess what? We're going to erase all of them anyway, except for the 2 we want to keep. That's called the bullshit principle.
In the case that we have water, this is a two-dimensional surface, they would be circles. But when you deal with light, you can think of them as three-dimensional, that means spherical waves.
Right, you can think of them as three-dimensional spherical waves, which would be conish bubbles coming out of the slit. A photon is making a coned bubble. No. I mean, intuitively, it doesn't make any sense, because I can take that same photon that's now a coned bubble, and I can make it go through something else, and it's just a tiny little photon still. How could it be a big coned bubble? It can't be.
Now, the Huygens-Fresnel principle is very powerful, though there is a wide range of opinion to its scientific merit.
Now, I love him for doing this, okay? Because in his 802 and his 801 lecture, you know, Huygens comes up and he doesn't do this. And I love that this shows some frickin' integrity at least. That he acknowledges that, yes, maybe this is bullshit. But in a way he doesn't, because in a way he's saying this sarcastically.
And in a very famous book, The Principle of Electrodynamics by Melvin Schwartz.
I'll have to look up Melvin because he's my kind of guy. M-L-V-E-N Schwartz. S-H-O-R-T-Z-W or something. Schwartz.
I read the following, and I quote verbatim from his book.
Thank you.
He says, Huygens' principle tells us to consider each point on a wavefront as a new source of radiation and add the radiation from all the new sources together. Physically, this makes no sense at all. Light does not emit light. Only accelerating charges emit light.
Yes, see, but technically an even better argument is that we have found nothing in the universe smaller than light. Electromagnetic radiation. You don't get smaller than that. You don't make something else you can radiate. You can't radiate something smaller than a photon. There's no evidence that anything like that ever existed or will ever exist or any of that crap. So it's just made up. The principle has nothing to do with any evidence indicating that this really happens. That waves make zillions or an infinite number of new little waves. There's no evidence anywhere in the universe that this crap has anything to do with reality.
Thus we will begin by throwing out Huygens' principle completely. Later we will see that it actually does give the right answer for the wrong reasons.
Exactly. So shouldn't see, that's something right there, and he should know this, that it is getting the wrong answer, the right answer for the wrong reasons. That it's completely fudge. It's completely a made-up gimmick to turn the single slit experiment into the double slit experiment. That's all it is. It's a gimmick. And you know, that, it should just be honestly stated that yes, this isn't good enough. If you're going to make something the foundation of your physics, you're going to talk about the fundamental particles in physics, you shouldn't have a gimmick as a thing that makes it make sense. If that makes your equations work, then your equations are broken.
So I will proceed my lecture today to get the right answer, but perhaps for the wrong reason.
Now, I don't know whether that was sarcasm or what that was, right? I don't know. But if you're a physics lecturer at MIT, you shouldn't be wanting to get the right answer for the wrong reason. That really should be a problem that just say, this is a problem physics has got to fix because this is bullshit. I'm telling you crap that's crap, and you're supposed to believe it because it comes up with the right answer by cheating.
Suppose now we have a electromagnetic wave. I'm particularly thinking of light. And I have here an opening, and I have here an opening, and plane waves are coming in from the left, moving with the speed of light. And let this opening be A, and let this opening be B. And here the center of the two is O. This could be a circular opening, it could also be a slit. Most of the experiments I will do today are with slits, which are perpendicular to the blackboard. So they are very narrow openings.
Yeah, I don't know if this part's very
Imagine
interesting.
now here a point P. And so the wave from point A will reach that point P, but the wave from source B will also reach that point P. And so the electric vectors there are going to be added, of course, vectorially.
Right, so he's just saying the wavelength, and so they're just using the electrical wavelength. It doesn't really matter. They're both the same way. They peak at the same point. Okay, the magnetic wave and the electrical wave. So it doesn't really matter. But regardless, so they're just using that as the definition of the wavelength, And what the wavelength could be is just the distance between the particles, if you understand them to be particles. Alright, so I think he's just going to do math now, so I don't know if I want to waste too much time. I want to get to the experiment itself, and this is the double slit stuff, which we've already done, which doesn't use Huygens.
Imagine now that BP minus AP, imagine that were 1/2 wavelength. Then what you get is that the mountain of the E vector here will coincide with the valley of the E vector from the other one, and so you will get the situation that light plus light will give darkness.
Right, so he says that all the time. That's a phrase he uses in 801, 802, and in 803. 25 lectures in each series. And so I've heard it many times out of his mouth. Light plus light equals darkness. And even that somebody should just pause and say, that doesn't make any sense. Darkness is where there aren't photons. There's no way you can make 2 photons invisible. And we know that where they peak, there's going to be twice as many photons. So I think it's quite obvious that light plus light doesn't make darkness. It's darkness plus darkness that makes darkness. There's no photons there. There's not that there's 2 photons there out of phase. There's no photons there. I mean, that's just logical. Energy conservation, photon conservation tells you there aren't 2 photons there interfering with each other, turning into nothing. That's not where they went.
Interference. The wave from here and the wave from there would be 180 degrees out of phase.
Alright, now I'm arguing that the fundamental problem with Professor Lewin's understanding of physics is they don't, or Einstein's, or anyone's, apparently, is they don't understand that the electromagnetic function is a function of a collection of photons. It's a material function. Something has to be a component of an electron, a proton, a neutron. It has to be one of these atomic components to possess electromagnetic function. Light, the radiation produced by electrons, doesn't possess any electromagnetic component. What it does is that it causes the expression of electromagnetic function, virtual photons, when they interact with electrons. So a stream of blue light goes into an electron containing many little photons at a higher frequency. A stream of red light would leave. The electron would move, and in moving it would expel magnetism as virtual photons. Now, if they understood it like that, all of this would make sense. No problem. But because they don't understand it correctly, they keep thinking that electromagnetic function is in a photon, and a photon doesn't have it. Again, I'll argue again, the photon is a thing that only has meaning, only has reality in the one dimension it's moving. That's it. It only has mass if you're here. If you're here, no mass. If you're up here, no mass. It has no mass in any other perpendicular dimension. Not this way, and certainly not behind it. It only has mass in the dimension it's moving in. That's it. It doesn't have any perpendicular components. Where an electron moving is doing something very different. As it's moving, it's expelling all the elements that are going the wrong way, and it's expelling them as electromagnetic fields. Okay.
And if you take all the points for which the difference is 1/2 lambda, that is a hyperboloidal surface. It's like a ball. Not only in the blackboard, but it also comes out of the blackboard. It's like a ball. Remember from your...
Yeah, well, this is just a phenomenon that you wouldn't really. It just has to do with where you place distance-wise, that proportionality of how to state that. But that parabola changes depending on where you place the screen. So it really is. It's a synthetic. It's a fake drawing. You can't do this. It's not really a parabola. In the sense that if you'd have to take it to an infinite distance to draw that parabola, so it makes no sense. So this doesn't happen in reality. I'm just saying, if I put the slit, if I put the screen here, 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 those will be consistent distances. They'll create a consistent gap. This parabola will not exist in those realities. It doesn't exist. You can't demonstrate that parabola by doing the experiment. So it's a mathematical function. It's not a reality function again. So that's another problem.
High school days, that if the sum of the distance AP and VP is a constant, then you get an ellipse. But if the difference is a constant, you get a hyperbola. So you will get a hyperboloidal surface, and everywhere on that surface, B minus AP would then be...
Like I said, that it has nothing to do with what actually takes place here. It just has to do with the fact that they're just finishing up with their conclusion that, okay, it's a wave, so now I have to explain how it has a phase change. So now they're just explaining the phase change of the photon. But the photon, it wasn't two photons in the first place, so none of this... It didn't go through both slits. It didn't do this. It didn't do any of this crap. So none of that crap has anything to do with reality. It's not a function of reality. It's a function of their mathematics again.
1/2 lambda. And then you would get the amazing consequences. Light plus light would give darkness. That's
See, he said it again. He said it again.
Tomatoes don't...
See, he said it again. He says it a lot.
...do that. One tomato on top of another tomato does not give no tomato. That is distinctly different from particles.
Well, again, if you do the single slit, what you will get with light is a bunch of tomato all over the screen, diffracted.
Now, of course, there are also hyperboloidal surfaces for which there is constructive interference. In other words, if I make this difference n times lambda, whereby n is either 0 or plus or minus 1 or plus or minus 2.
It just means that he's moving it to the... See, they just use this arbitrary one. By identifying these locations with a number, then they just multiply it times the wavelength to decide how far it is away. So it's just... It's... You know, this looks a lot more complicated than what the actual statement is. The n is just basically saying there's a consistent different distance consistent with the wavelength of the light that these locations will show up with. So you'll have complete destructive interference, then complete constructive interference, then complete destructive interference, then complete constructive interference, and that's all these n numbers mean. And it just makes their math work, is because they use this artificial identification symbol of 0, 1, 2, 3, 1, 2, 3. By using those numbers, it just makes it really easy, right? Because you just go, well, how far away is it? Well, it's 3, so it's 3 times away. Yeah, duh.
Then I would get surfaces for which we get constructive interference. Then the phase difference between the two waves is either 0 or 2 pi or 4 pi. So we have surfaces with constructive interference, and then we have surfaces with destructive interference, and that's going to be at the heart of what I want to discuss with you now. So I will start a new drawing. I think we don't need this anymore. now have a screen with two narrow openings. They could be slits, as I said before. So here is one opening, and here is the other opening, and let the separation between them be D.
Alright, so this is something I've pointed out before, but this is another one of the canards of the whole way they describe the single slit and then describe the double slit. So not only are they cheating by pretending water does something that's the same as this, which it isn't, when they do the double slit, there's a certain gap here. Okay, so we know that this center impediment, he's drawing this totally wrong proportions, right? The slits are much more closely related to the width of this thing here. So they're almost, this is smaller or the same size as the openings, not this. But anyway, the point is when they do the double slit and the single slit by comparison, they don't use the same opening total. So what they do is they'll do the single slit with this only one of these slits as the dimension, and you get clearly a much more diffracted pattern in the single slit. So as you widen the amount of space that's open, the gap opening, you close in the entire pattern, so it gets tighter and tighter, and you get more and more bars are visible. So as you make this narrower and narrower, less and less bars are visible, and you end up with just the central maxima as you go wider and wider. So that's sort of another little cheat used to make one pattern look different than the other pattern. If you use the same gap total in a single slit, so just add this total plus this, and then do a single slit experiment with exactly that same amount of gap, then you'll get a pattern that will be identical in all respects except the central maxima of the single slit will be much brighter, quite obviously, because there's no impediment blocking the central light. But that's the only difference in the patterns.
And the upper one is we call source number 1, and the other one source number 2. Suppose now that we are looking at this at a distance which is very far away. Very, very far away.
Which helps to eliminate the distortion that will be created by the light actually coming from the slits. This is a very small, like, a couple of millimeters in length, this whole experiment. But by making it far away, the direct light that went straight, that didn't get diffracted, will become minuscule by comparison to the rest of the pattern. So you'll only see the diffracted segment, only the thing that has an angle. The angles will be multiplied. So you can sort of understand that a straight line is a straight line. No matter how long I make it, it's the same width. But anything that has an angle, non-parallel to that line, as I go further and further away, the gap gets bigger and bigger and bigger. So, I mean, obviously, this is multiplied in its effect, and the straight stuff is not multiplied. So obviously this diminishes in importance, and this becomes more obvious in importance. So the further away you go, the more you eliminate all the straight line component.
And where you are located in space, seen from this point, is an angle theta. So the wave from this source will reach you, and since that point is very far away, these lines here are of course parallel to each other. Very close to parallel.
Right. So this doesn't look correct because it has to hit one point out here. But the point is you can't draw that. You can't draw these proportions in proportion. So what's happening is you're stuck with either drawing it accurately that they're essentially parallel, which they almost are, or you're stuck with making them into a point, which is sort of distorting what's happening because they're really parallel lines in the math. So there's no way to win when you try to draw this, because you can't make this as big as it needs to be by proportion to this. This needs to be a tiny, tiny little drawing over here, and this needs to be big over here, and then you can make the lines, and then you would notice that even though they have a slight change in angle, they're almost parallel.
Because it's very far away. The wave that comes from this one has to travel over a larger distance than the wave that comes from this one. And that difference can easily be expressed algebraically. If this angle is 90 degrees, that difference is this much. That is how much further this wave has to travel than this one.
Right, now you can understand that in the sense that, see, people just keep messing this up with this wavelength thing. So a photon is a really tiny thing, in the sense I could get zillions of them to go across the top of my finger. So they have very little low profile when they're coming at you, but they're long. So in a sense their wavelength is much longer than their width or height, so to speak, if I could say it in those terms. They're deeper than they are wide or tall. And nobody really explains that. So this component is pretty big when you think about it in terms of the tininess of a photon. So you could put in the length of a wavelength, you could shoot a million photons through the length of a photon's wavelength. They're really small. And the reason, see, they're not technically long. It's just, again, it's because they don't understand what a photon is that they think it's some sort of long wavy thing. It's not. It's a photon, and then there's a period of time, and then there's another photon, and then there's a period of time, and there's another photon. And they're calling that a photon. But it's really 3 gravitons, or 4 or 5 or 10 in a row.
And then they vectorially add very far away at the location where you happen to be. And this difference here is d sine theta. That's immediately obvious. If this angle is theta, this angle is also theta. So the path difference is d sine theta. And that translates...
So it's that distance times theta, the angle, which just changes it to a proportion, so it's the distance times some percentage. So you're basically just cutting some hair off of that distance.
Into a phase angle difference between the E vectors. Theta. First of all, d sine theta, which is the path difference, this is how many wavelengths you can fit on that path difference. So I divide it by lambda. And for each wavelength that I can fit on there, the phase difference is going to be 2 pi. And so the phase angle, the difference between the wave from here and there, is therefore 2 pi times d divided by lambda times sine theta.
Alright, now I think that is just doing it more complicated than just saying what percentage of a wavelength is this distance. So if you just take the d and say what percentage of a wavelength is this distance, is it 25%? Is it 1.25%? Is it, you know, multiples of a wavelength, or is it some percentage of a wavelength? And you don't need to do the doing the 2 pi thing and then multiplying it, but they're just doing this as a what percentage of a wavelength is this amount, and that's all it is. So I don't think you have to do anything more complicated than just divide the distance into the wavelength.
And so now I can set the condition for constructive interference. Constructive interference.
Okay, so I'll jump ahead here because I think you do understand that. You know that he's just going to do the end thing again at different positions. You're going to have the thing, and he's just going to run through that. And there's no Huygens here because it's all double slit. So let's see. I'll move up a little further.
Now you may think that that is rather small. Well, you will see that that's what you need. You need very small values of d to even see this phenomenon. So now let's evaluate what n is. Let's evaluate what delta is. evaluate what the
All right, let's
sine
go back a little further because this looks like we're just getting
That's
into
the
a little
light I
bit.
will use.
So he's going to do a
So
single
here I
slit.
use two openings. So light
All right,
goes
it's
in from
two.
the left. And let this distance be L.
Okay, so it's the two slit.
And so
Two
I want to
openings.
know if I look under an angle theta, as seen from the slits, I want
And again, this would be N1, this would be N1, N2, N2. So again, those numbers are just being used to define a proportional wavelength difference. So it's just basically how big is one wavelength represented, magnified on this wall. So you're just really doing the magnification thing, which is you take the angle times the side, and that way you figure out the height of this distance. And that's basically just telling you how big something small over there looks over here. And once you have that, then you're just multiplying it times 1, 2, 3, 4, 5 to find the distances. Okay, so again, let's see if we get to the experiment itself. Let's see how far along he is.
but you will get the first maximum, the blue here.
Okay, so
you'll
he
get
drew that, which is not very accurate.
just like this. And that translates then into an x value of about plus n minus 1.2 centimeters.
So
now I
these
know
are
what
just the
sine
points
theta is,
where,
and I use the small angle approximation, which is more than adequate. And I know now where on this screen I get again maxima. And that is then here, 1.2 centimeters on this side and 1.2 centimeters on the other side, because you get, of course, plus as well as minus. And then I can continue for n equals 1, n equals 2. I will just do plus or minus 10. So then you get here plus or minus 20 pi.
yeah, we know that. I'm just saying, why are you doing that?
On the shape of the dark and light areas that I'm going to see. So what I plot here now is, I will lower this and I will raise it later, because I want to work above my head so that you can see what I'm doing. So I'm plotting here the sine of theta. And keep in mind that it's linearly proportional with x. But I always prefer to plot the sine of theta. And so here is 0. Let here be lambda divided by d, and it's where my first maximum will come. You can see that. And then here, the same distance, I have 2 lambda divided by d. And on the other side, I have minus lambda divided by d. And all of these are maxima, constructive interference, and the destructive interference clearly falls smack in the middle.
Right, so this is just N2, N1,
And
N0.
so the destructive interferences are here. And so you get light curves, light intensity, just like this. Light intensity, remember, is always the pointing vector.
Right, so I mean right here, this is, this is not accurate. So again, it's just wrong to say that that's how the experiment comes out, because it doesn't. Clearly the central maxima was going to be 4 times brighter than these in the double slit experiment. It's 8 times brighter in the single slit. But I mean, there's just no point in drawing it like that, because that's not how it works. It does diminish as you go wider, logically, intuitively.
Intensity, and that is in watts per square meter.
So he's claiming that the photons, the amount of photons that hit here, are in the watts. I mean, it's just, I don't know how you can interpret that as accurate. It's just not.
Now the first thing that I want you to notice, and you will see that today.
Now, it might be in the bulge thing, you know what I'm saying? You might be able to say that the bars in this section are all equal, but there's no way to say that because they quite obviously diminish as they bulge down. So there's just no way to make sense out of this as an accurate representation of what happens. And I'm just saying that this is a problem. That's not how a physics lecture should work.
In various demonstrations, is that the location of the maxima depends on the wavelength.
So that's all he's saying is yes, red light would have a higher frequency, so obviously they'll be closer, so let's skip that. That's just a,
650
see, just
very close to
different colors will be different places.
So each lives a life of its own.
Right, so and when the two of them, if you multiply, you
The
know,
light intensity that you see is a cosine square, of course, very close to the same. Remember, E is proportional.
okay.
And so you get the square of this term and the square of this term, but the average of the square of this term is 1/2, so forget that for now. And so you see it is going to be proportional to the square of delta over 2. And so this function that you see, delta, is linearly proportional to sine theta.
Let's just move ahead a little.
This is where it is. You're going to see it there. And in order
Okay,
for
so
you
this
to
is him
see
doing the
it,
experiment.
you have to make it.
Hopefully this camera will hold out a little longer. Yeah, it's looks like it's going to run out of life. Unfortunately, right when I need it. Battery's getting low.
When you look here on the screen,
So there it is.
you will see areas.
Okay, so let's just quickly point out. See these things at the end here? That's not in the math anywhere. He just drew a line that showed these all the same size. Obviously their intensity is much lower, diminishes almost to nothing, then gets brighter again, diminishes to nothing, gets brighter again. There's clearly, this has nothing to do with what he just did on as mathematically. And you can also see that it's also spreading this way, which is interesting that you're getting little diffraction lines you can actually see in the tops of these. So his slit must not have a very high, must not be a very high slit. But clearly it's there. It's faint, but you can see it. I can see it on the camera. That's the traditional two-slit experiment. And again, if you use the same width of dimension for the single slit, you'll get exactly the same pattern. The only thing that's going to change is this is going to be the central maxima. Will take up the space of 1.5, well actually 3 units. So 1.5 of these units will blend together because there's going to actually be the dark space will be in the center and it's going to get wiped out by the opening, and then you'll have the two sides of the bright. So you'll have, this is out of phase in the single slit, this phase will be different, and there'll be a dark line here that'll get wiped out by the light going straight through, and these two, it's like these two will be merged essentially, but they're going to be closer together, so it's not going to really be the same merger. But the point is this will all be the same. The only thing that changes is this one center area. And that's the facts. So I guess I'll make another video in the future at some point and go through what he says during him doing the experiment here. But again, Huygens didn't come up anywhere. You know, no discussion of Huygens at all. And so he doesn't do the single split in this lecture, so we don't get to, you know. But I've done that one before. I've played the video where he makes it wider and wider, and it gets wider and wider, and blah, blah, blah. It might be in here, but I'm not sure if it's in this lecture. But if it is, I'll play that again. Well, I don't know. I shouldn't bother doing that again, because I already did that one. So